ammonia can be generated. There are two processes here, both a direct process, forward process, and reverse process can be used here. So hydrogen also we can generate through this process, which is from the ammonia, so that this is also decomposition of ammonia also needs this heat. That heat maybe we can take from the solar energy concentrating collectors, or maybe we can take from the waste heat recovery. And coming to this application, yes, once you generate the hydrogen, because hydrogen, not only hydrogen, it gives so many other products also. So these multiple products of this hydrogen fuel generation, that leads to many inventions or ideas, so that how to use this the hydrogen into various forms like heating, cooling, and electricity generation and transportation, cooking, etc. So that leads to the multiple generation of this as per the demand of the customer. That this multiple generation of this product can be plant, can be, or process can be designed based on this hydrogen energy. That plant name is called as power generation. If you see the power plant generates the electricity that for giving one energy is mostly the fuel is energy, that calorific value, and the fuel that we are converting into the heat. That heat is various forms of energy, it is converted, finally it is giving the electricity. But that results a lot of heat, that means heat waste. That's nearly two-thirds of the energy is wasted, and only one-third of the energy only we are able to convert into the useful form, that is electricity. So if this power plant can be extended to the cogeneration form, that's so whatever the waste heat is there, that two-thirds of the waste completely we can't recover, but at least some part of the waste heat can be recovered into the process heat, so that cogeneration efficiency is energy conversion efficiency is higher than the power plant efficiency. But if it is we are adding some cooling production, because you know very well the cooling production has the higher COP. COP means it's one form of this efficiency, coefficient of performance we are defining for the cool to define this cooling performance. Obviously, we know the for this vapor compression refrigeration system, the COP is higher than 1. That means what it means of this higher than 1, that's more than 100%. So if this cooling is also, if you are able to integrate to this cogeneration, that means apart from the electricity and process heat, so it is the third output is the cooling production, then it may be renamed into the trigeneration. The benefit of this trigeneration compared to the polygeneration and the cogeneration is it gives the higher efficiency, because of the term we are adding this cooling, that's and also the efficiency term we are adding the coefficient of performance. That's why very close to 100%, or sometimes it may be more than 100% of the efficiency, energy conversion efficiency I am saying, because the terminology will change from power plant to cogeneration, and cogeneration to that polygeneration, especially for the trigeneration what we are calling, that's energy conversion efficiency, energy utilization factor or something like we can call. That may be possible to close to 100% or more than 100% it is possible. This trigeneration still it can be extended to various other forms of these outputs like desalination, water purifier, and fuel production, so that hydrogen can be connected to the fuel cells. Again, fuel cells can be used to generate the water as well as this electricity. There are many such type of productions, heating, cooling, electricity. We can design this based on this either solar energy, waste heat recovery, or mixing of different energy. Either it may be single source of energy, or it may be hybrid source of energy like biomass, wind, fuels, geothermal, etc. So this hydrogen can be connected to this poly generation, especially this process plant. I'm sharing very two three ideas only, but the readers here, faculty or the researchers here, that they can design a new layout which may not be existed, that may be customized. We can design this hydrogen based poly generation, thermal poly generation, that may generate the required outputs. Coming to this gasification route, especially this hydrogen based this thermal poly generation, if you see this gasification, the feed is a solid fuel. It may be coal, biomass, or whatever it may be. This gasification may have this air gasification, or it may be steam gasification. If you are supplying the restricted amount of air, you know very well, this gasification process is a partial oxidation takes place inside this reactor, which is a restricted amount of air or the oxygen is supplied here. Apart from this air, if you are also supplying the steam, if you see this drawing on right hand side, that steam also has been supplied to this gasifier, so that steam leads to generate more amount of hydrogen, because the steam H2O, H2 has H2, that leads to increase the yield of this hydrogen through this gasification route. So steam gasification is better than this air gasification, especially while focusing on the hydrogen generation. That's why here this gasification we are adding the steam gasification. In the steam gasification, the output, if you see, byproduct charcoal is a bright byproduct that's coming from that the bottom of this gasifier. The charcoal also one of the fuel may be used for the cooking, or maybe for further processing applications, thermal applications. This producer gas, at the top, if you see the gasifier, that producer gas is used, that came enriched, or it is cleaned by water, and it is temperature is brought down. That can be directly used to drive the engines, that means gas based, that's gaseous engines, to get the electricity. And there are many other options. If you see IGCC plant here, if you see this IGCC plant is used for the production of this electricity. IGCC means integrated gasification combined cycle power plant. Generally, gas power plant means combined cycle power plant demands the natural gas, but without using this natural gas, using this solid fuel, we can drive the gas power plant. Generally, if you see these gas turbines demands the gas fuel only, but not the solid fuel. But by incorporating this component, that's reactor gasifier, we can convert the solid fuels into gaseous fuel. That gaseous fuels directly it is used, supplied to the gas turbine combustion chamber, that generates the electricity from the gas power plant, as well as this there is a waste heat recovery is there, heat recovery steam generator. Through this HRG steam is generated, that steam also gives this electricity. And coming to this hydrogen production, if you see at the top part, bottom part is giving the electricity generation through that gas power plant, steam power plant, of course the fuel cells also. But this fuel cells demands this hydrogen. How to get this hydrogen? Yes, this hydrogen can be generated using this shift reactor, synthesis of this gas converter. That shift reaction is giving this hydrogen. But this hydrogen, apart from this hydrogen, carbon dioxide also it is generating. Carbon dioxide can be separated through this chemical route, and that can maybe sequestration may be added, integrated to this plant, so that hydrogen alone can be separated. That hydrogen can be used in the combustion chamber, which is for the power generation, or it may be directly supplied to the fuel cells to generate this electricity. So that if you see the output from the poly generation, it gives many main primary product is from the poly generation is the electricity, of course. But apart from this electricity, you can also see the process heat, cooling, and desalination, hot water, fuel cells, this drinking water, etc. The finally, what benefit we can get here because of this multiple generation from the source, especially for the coal, the overall utilization factor, that's energy utilization factor, energy conversion factor will increase by means of this one. And focusing of this gasification route, earlier slide shows this gasification, that's a partial oxidation. Next question is how to solve this gasification. That means how to design the reactor, how much hydrogen or how much producer gas we can generate. Let us say 1 kg of fuel, 1 kg of coal or the biomass has been supplied. How much amount of this feed is required, that means air is required, and how much amount of these inputs are required, that means so that outputs can be simulated using these models like thermodynamic equilibrium model. Both energy model as well as exergy model can be applied so that we can develop the process conditions that can optimize to increase the yield of hydrogen as well as increase the yield of the producer gas. That means based on the objective function, that system can be processed. Let us say the gas is rich gas is coming, automatically power generation also will be increased, that can be maximized. In this gas composition, syngas composition, if you see the products like hydrogen, carbon monoxide, of course the fuel also will come, that means maybe unbound fuel like CH4, and products like carbon dioxide, nitrogen will come here. And this 19.5, 20.3, these are the syngas composition, that's what gas composition. This gas composition experimentally we can measure by means of these instruments, gas composition instrumentation, or we can also develop some models. That models will simulate this gas composition through the gasification composition. Also we can estimate the quality or the output energy in terms of this calorific value or in terms of this various process like energy or exergy of this output. This the first At the first step we have to I didn't model the mathematical model as well as the simulation that gives the gas composition. This gas composition, if you see this mole fraction of the syngas, it's by dry flue gas analysis at various conditions like air fuel ratio can be changed here, but of course this is the restricted amount of air is applied here. So once you are changing the air fuel ratio, the steam fuel ratio, because once you increase the steam, the hydrogen production is increasing here. If you see this second drawing, the steam fuel ratio is increased, so that hydrogen yield is increasing in the gas composition. And the CH4 is actually this is a small part only, it's less than 5% only, approximately you can get the unbound, that's a CH4, that's a methane. And the first drawing shows this air fuel ratio, second is the steam fuel supply of steam, and last is the pressure. Because why it is pressure gasifier, mostly for the, if it is supplied for the IGCC plant, definitely that has to work out at the pressurized system, that's compressed air is supplied into the gasifier. Because if it is an incineration process, that's atmospheric fluid as bed gasifier we can see, but this is a pressurized gasifier. In this pressurized gasifier, that's pressure is approximately 10 8 8 to 10 or 11 bar also we can maintain. That depends upon the pressure ratio of this gas turbine. That's if you see the compressor in the IGCC, that takes the atmospheric air and it compresses to the combustion chamber pressure, which may be 10 bar or the 11 bar. So here that gasifier pressure is also is increased here, some 10 to 20 bar. 20 bar is hypothetical actually. Most of the power plants, they are running at 10 to 12 bar only, because that is the optimum pressure. At one optimum pressure only we can get the maximum efficiency, and also more production of the electricity is possible through this optimization process. And next is one more idea is here, not only the coal, because nowadays issues are coming, because the utilization of this coal or burning of the coal in the thermal power plant is due to these restrictions by the state government as the central government. We have to control the use of this coal. That's why instead of completely shut down of these coal power plants, either thermal or the gasification route, slowly we can shift from slowly, that means smoothly, we can shift from the traditional conventional usage of the fuels to non-conventional fuels like solar, biomass, etc. So that's why the co-firing, this is called as co-gasification. The co-firing is used for the incineration process like thermal power plant. If you mix the biomass to the coal, that come furnace, that process is called as a co-firing process. And in case of gasification, if you combine this coal and the biomass, that process is called as a co-gasification process. In co-gasification process, biomass to coal, that means the amount of biomass is increased in the x-axis from 0 to 1. That means 0 means it's no biomass, it's completely the coal, and 1 means that's completely the biomass. Coming to this hydrogen production, the biomass to coal ratio, one that of course that depends upon the biomass composition, because we have varieties of biomass here. So that depends. This curve also depends. The characteristic also depends upon the quality or the composition of the biomass, solid biomass. So here, interestingly, the biomass to coal ratio is increasing of this biomass to coal ratio. The hydrogen yield is increasing in producer gas. The hydrogen yield is increasing. So the in subsequent process, hydrogen along with this producer gas we can use, or maybe it can be processed subsequent process like carbon dioxide can be absorbed as a sequestration process. So that's why there are many varieties of applications we can see. It may be the enriched process, that means the calorific value is increased by means of this reforming process, or maybe completely carbon dioxide can be absorbed, so that we can also design a zero emission power plant. The concept of the concept of this zero emission power plant is, that means output is electricity only, but there is no any carbon dioxide and there is no any emissions like NOx, SOx, nothing is there. Uh, that means if you see the hydrogen, if the hydrogen is bound with oxygen, H2 and O2, what is the result here? Electricity plus water, same like fuel cells. In the fuel cells we are supplying the hydrogen as a fuel, so that product is water may be used as the desalination process, subsequent process, but the main product is the electricity. Similarly, in the combustion route also we can design such zero emission power plant. Hydrogen is bound with oxygen, so that gives the H2O, but the H2O we have to condense. So that's why, whereas there are many different options we have, I will explain one by one, and so how to design such type of zero emission power plants. And this gasification, as I mentioned, without separation of this carbon dioxide from the producer gas, if you see this gasifier, a small part of this gasifier I'm shown here, because the main focus is given here on the heat recovery steam generator. If you see this vertical heat exchanger, it may be either horizontal heat exchanger or vertical heat exchanger. This is a GMR energy layout. In the GMR energy layout, the heat exchanger, heat recovery steam generator, waste heat recovery steam generator is a vertical so that saves the floor energy. That's installation floor area. It is the three pressures here, that are the high pressure, intermediate pressure, and the low pressure. In this heat recovery, steam is generated through this gasification. So through this gasification, the fuel is the solid fuel, and steam is also is required. That's why some part of steam, if you see the steam injection, some part of the steam has been taken from the turbine, steam turbine. That steam has been injected into the gasifier. This steam is injected in the gasifier so that we can ensure the hydrogen rich gas, that's a syngas. The hydrogen rich syngas is directly bound into the gas turbine combustion chamber, and also the supplementary firing. The supplementary firing is option actually, because sometimes we need to supply the electricity during this peak condition, especially in the summer. That's beyond the capacity of the power plant. If the power plant is designed for let us say this is 380 megawatts, without increasing the means without installing the another extra power plant with the same capacity, we can generate. It is possible to generate the 400 megawatts or 400 plus megawatts. That's why that time we can simply switch on to this supplementary firing option, so that the supplementary firing options, once the demand is increasing, that means it takes the additional amount of this fuel that has been supplied in the duct top at the inlet of this heat exchanger, that's a heat recovery steam generator. But if you see here, there is no need of supply this air for the oxidation, because already the compressed air, if you see the atmospheric air is entering into the compressor, the compressed air is supplied to the gas turbine combustion chamber, and some part is going to supply the part restricted amount of air is supplied to the gasifier. There is more amount of air is supplied to the gas turbine combustion chamber, because the air fuel ratio in the gas turbine combustion chamber is very high. It's 45 up to sometimes 50 is to 1 also is there. Therefore, huge amount of air is there in the gas turbine combustion chamber. That's why in the products, that means in the products, more amount of oxygen is there. That's why in the supplementary firing, no need to supply the additional amount of oxygen or the air. That's why directly the flue gas is directly, because that is enough amount of oxygen, so that fuel alone, the producer gas alone can be supplied in supplementary firing. But the air fuel ratio in the gasifier, it is low. It's not like gas turbine combustion chamber, it is a 50 to 1, but it is the gasifier, it is very low value, because it is a restricted amount of air is supplied, that is a partial oxidation takes place here. So this is the one of the application, that's biomass based IGCC integrated gasification combined cycle power plant, so that more amount of hydrogen we can ensure in the combustion chamber, because that's more amount of hydrogen in the producer gas that ensure, that means calorific value will be increased, and the cleanliness of the combustion also will increase. But the solution of this gasifier, especially for the restricted amount of air, that's which is called as partial oxidation, it's complex. Why it is complex? If it is a full combustion, the full combustion means that we are supplying either air or maybe oxygen alone we can supply. If you have the air separation plant, that means oxygen alone also we can supply into the combustion chamber. In the full combustion, if you see the full combustion, the products are the carbon dioxide, H2O2 and N2. NOx also we can solve if you have the NOx model. Here no need to use the numerical methods, because this is a completely the linear equations. The complete combustion, either producer gas or the biomass combustion, the complete combustion takes place with the linear equations only. So solving these linear equations, that's the coefficients like b1, b2, b3, b4. In case of NOx, one extra is coming, NO2, the C5. These equations are simple, simply by coefficients, that's mass balance and energy balance, that is sufficient to solve these equations, because energy balance based on this temperature, combustion chamber temperature, or maybe air fuel ratio, either air fuel ratio or given combustion chamber temperature, we can completely we can solve these equations. But if it is a partial oxidation, like this gasifier, this is a downward gasifier what we have in the earlier university, this downward gasifier that generates electricity. In this downward gasifier, if you see the uh, gas, that's product gas, that's which is also gas in gas, it has so many compositions like CH4, CO, CO2, H2, H2O, N2. The supply is a fuel, that's solid fuel, that's a CHON system. It is used for the simple thermal model. That's why it is converted into A1, A2, A3, A4. The air is supplied for this restricted amount of air is supplied for the partial oxidation, and steam also has been supplied for the enriching of this hydrogen in the producer gas, which is B4H2 is that focus on the hydrogen, and it may be dry fuel or it may be wet fuel. With the wet fuel, moisture content also we have to add this fuel. But mostly this partial oxidation, what grounded gas were in the background figure, what we are seeing, what are the biomass is there, that biomass is completely dried before supplying to this downward gasifier, so that the moisture content is minimum, I can say. It's but according to the measurement or the calculations, the moisture content also we can add into this model, this thermochemical model, so that we can solve all the results like B1 to B6. If you see the B1 to B6, there are six unknowns are there, and earlier there are four unknowns, that's B1 to B4 only. That's easy because you can find this C balance, H balance, O balance, and N balance. But here, apart from this mass balance, we also can use these energy equations. That energy equations involves the temperature of this combustion. But apart from this energy balance and mass balance, we also need some additional equations, because if you see internally what is happening here, cracking, reforming, shifting reactions takes place. That's why these coefficients completely we can solve by using the dissociation constants, because inside this cracking dissociation takes place. That's why these dissociation constants can be taken from the first equation is the reforming equation, which is CH4 is in association with the water H2O, or the steam that is reformed into CO and hydrogen. And similarly, this inside carbon monoxide is there. Carbon monoxide also it is reformed in with the presence of this steam, that's which is H2O, into the CO2 and H2. Finally, this H2O can be removed or it may be retained as it is for the complete combustion, according to whether it is a zero emission power plant or not. So finally, once we are integrating with these two constants, these two equations, we can solve this equation completely. That's all these coefficients B1 to B6 can be solved here. But here these dissociation constants are non-linear. If you see the Kp1 and Kp2, that's the dissociation constants respectively for the reforming equation and the water shift reaction. These coefficients can be that's Kp1 and Kp2, which is a function of temperature, that may be modeled. We can take in from the either properties, thermochemical properties, or we can simulate it according to these correlations. So this is a why it is called as non-linear equations. You can see the cubic form and square, and in the second equation also it is a multiplications. It's mostly non-linear. That's why numerical methods we have to apply to solve these equations, that's coefficients B1 to B6. So in this model, B1 to B6 are completely condensed into two unknowns, that's B1 to B2 only. So that the function 1 is a B1 B2 and function 2 is also B1 B2. So that finally this equation is condensed into two unknowns, that is a B1 to B2 only. After completion of this, applying these numerical methods, we can find the results of B1 and B2. That B1 and B2 can be extended to find this B3, B4 and temperature completely. The gasification can be solved using this numerical method. We applied this Newton-Raphson method effectively so that more accurately and within fast time also we can expect the solution. So that's a completely composition, hydrogen composition, and of course other the gas compositions also CH4, CO, CO2, and nitrogen also we can get through this model, thermochemical model, that gives the composition as well as this the heating value. Apart from this heating value, we also needs this temperature, that's whether it is a actually the actual combustion chamber temperature and the adiabatic temperature. This adiabatic flame temperature is the maximum temperature. At the hypothetical condition, if you are burning this fuel, that adiabatic flame temperature also we can get it. And this oxidation, through this partial oxidation, what is the actual temperature also we can measure if it is experimental setup, or we can also simulate from this model, that is thermal performance prediction model, which is based on this biomass based IGCC, the power plants. And another option is chemical recuperation, as mentioned earlier. Method is solid fuel has been used. From the solid fuel, it may be coal or the biomass. We can generate the hydrogen rich producer gas. Once if it is a fuel is a gaseous fuels, especially the natural gas, for example, if it is a natural gas, mostly natural gas CH4 is a major element. It more than 90% or more than 95% of the composition you can see in the natural gas is the CH4. That's why CH4 has been taken as the main fuel in this chemical process. Coming to this plant layout, that's a chemical recuperation cycle, which is similar to the IGCC. Here also you can see the two power plants, topping cycle, the gas power plant, and also bottoming is a that can be extended once it is going to the combined cycle power plant. It's not shown completely the cycle. If you see the gas power plant, the water has been supplied to the waste heat recovery. This is the waste heat recovery consists of economizer, evaporator, and superheater. In this waste heat recovery, the temperature of water is increased so that it generates the steam, and steam has been combined with the steam is injected in this reactor in the lines of the CH4. So CH4 and steam has been reformed. That CH4 is reformed into hydrogen rich fuel. So this hydrogen rich fuel has been supplied to the main gas turbine combustion chamber, and also the reheater. If it is a reheat based run, that means Brayton cycle, that's high pressure gas turbine, the low pressure gas turbine. According at the appropriate pressures, if you see that fuels are at high pressure, the fuel is supplied in the gas turbine combustion chamber. At the low pressure, that's corresponding pressure, that's hydrogen rich fuel has been supplied with the reheater, gas reheater. So in this process, MSR, methane steam reformer, in this methane steam reformer, what is the fuel used for to get this hydrogen rich gas is a energy is required here. That heat energy is required. That heat energy has been taken from the uh, waste heat recovery, which is coming from the gas turbine systems. With the solar based system, solar integrated system, instead of using this waste heat recovery, because that waste heat recovery also we are using for the steam generation, instead of getting penalty from this waste heat recovery, we can also integrate with the solar system, so that solar system, that's thermal energy can be used apart, that means that water can be, steam can be integrated, so that more hydrogen can be generated either from the waste heat recovery and also from the solar concentrating collectors. These are the some of the models, that's rate of methane conversion, how it is converted into this reactor, methane reforming reactor, as a function of temperature at and also pressure, because if it is the atmospheric pressure, if it is the 1 bar, how it takes place, if the pressure is increased, another example of this pressure 15 bar is taken, so that how it is converted, that conversion, if you see the increasing of this temperature, that's reactor temperature from 300 degrees centigrade to 1000 degrees centigrade, the conversion is increasing. That means it is a y-axis, it is a showing this unconverted methane per 1 mole of this CH4. Through this chemical model, what it is described in the earlier slide, through this chemical models, that can be applied to find this gas composition, so that that gas composition will say how extent it is converted, that's conversion process is effective or complete or not. So with the help of the parameters, especially the process temperature and also the process pressure, can be studied, analyzed with this model, that's a thermochemical model, so that the effective process conditions can be recommended to get the more yield from this methane reforming process, which is also called as the chemical recuperation process. Another option of this using of hydrogen is a zero emission power plant. This is a one of the power plant layout that will use the result is water as well as electricity. There is no any carbon dioxide, because the carbon dioxide is completely dumped into sea or air, that is which is called as a carbon dioxide sequestration. This layout shows this use of this methane or the natural gas. That natural gas has been converted into the hydrogen. Various process, like if you see the at the beginning, the methane has been compressed, because this methane has to be compressed, and to the pressure has been increased to the required pressure at the gas turbine combustion chamber. And similarly, at the gas turbine combustion chamber, oxygen is supplied. Instead of supplying this compressed air, and the oxygen air separation plant, in the air separation plant, oxygen has been compressed. That compressed oxygen is supplied into the gas turbine combustion chamber. So the compressed methane, which is compressed natural gas, and also compressed oxygen has been supplied in the gas turbine combustion chamber. After that, after burning, this see the CH4 plus O2, that results to carbon dioxide, and H2O, that's water vapor or the steam, but both are combined form. That has been expanded in various process, like high pressure turbine, gas turbine, and gas reactor, intermediate pressure turbine, and low pressure turbine. And finally, subsequently, what happens here, that that gas, that's what we can call as exhaust gas, has been condensed. After condensing, what happens, because this is a mixing of CO2 and H2O, the H2O is completely condensed, because it is not possible to condense the carbon dioxide, CO2, which is the gas, but the vapor, which is H2O steam, that can be condensed, which is water, maybe as one of the byproduct from this zero emission power plant. So carbon dioxide alone, the gas alone, can be compressed. See, at various process it is compressed, and finally it is injected into the well. So this is the carbon dioxide sequestration process. So finally, this zero emission power plant results this results the electricity without any emissions like carbon dioxide emissions. The fuel is methane, or maybe directly hydrogen also we can supply. Once it is hydrogen is supplied here, there is no need of this carbon dioxide sequestration process. But as mentioned in the earlier at the beginning, most of the hydrogen we are generating, nearly 50% of the hydrogen we are generating through this reforming process from the natural gas as the main resource for the hydrogen production. So methane or the natural gas is directly has been supplied to this gas turbine combustion chamber, so that in subsequent process we can remove this carbon dioxide. The pre-combustion, post-combustion, there are many such techniques are available, because sometimes the pre-combustion we are treating the, like gasification or chemical recuperation, and post-combustion, after the combustion, this treatment has been taken here, so that carbon dioxide has been removed from this mixture of this H2 and CO2. These are the many layouts. Actually, the we have, depending upon the that means novelty, that means depending upon the requirements, we can design the various layouts of the zero emission power plants. Based on this zero emission power plant, it may be directly natural gas based, or maybe solid fuel also we can use to design the zero emission power plant. So either solid fuels or the gaseous fuels can be used to design this such type of zero emission power plants. And the renewable energy like solar energy, solar thermal, solar PV systems, that can be integrated to to generate the hydrogen and water desalination and electricity and transportation. There are many such poly generation systems we can generate using such this type of ideas like gasification process and reforming process. Then finally, that how the thermal poly generation is there. Yes, earlier thermal poly generations are through this IGCC model. Apart from this IGCC model, there are many other modes of this poly generation also we can design. Maybe without combustion systems also we can design such type of thermal poly generation systems. Because it has interesting highlights of this minimizing the losses. Of course, there is a one challenge is there while designing this thermal power generation. Justification is one of the challenge, because once you are adding some elements like process heat is added and cooling element is added, and water purifier process is purification process is included. So by adding these elements like n number of elements, the cost of the system will increase. That means whatever the investment we have, that investment has to be justified by the proper profit, whether the economically that profit we are getting or not. That economic justification, of course, the thermal justification gives this, technically we can justify thermal and thermo-economical and this exergy etc. routes. But once you are integrating with these economics, especially thermo-economics, that gives the results which is more feasible. Whether that idea is feasible or not, we can get the through this addition of this economic analysis. That means justification is one of the important thing that we have to integrate to this thermal power generation. Whether that idea of this thermal power generation is feasible or not, we have to cross check at the right from the beginning itself. And as I discussed three models like zero emission power plant, chemical recuperation, and there is a lot of flexibility. There flexibility in use of these energies like conventional energy, non-conventional energy, and flexibility in use of these layouts, different layouts. That also we can, that innovation is possible and research is possible. This type of such type of with the such type of flexibility and integration is possible with this thermal power generation. This is compact size. The compact size that depends upon the what type of components we are selecting. We are selecting. Let us say one of the GMR energy. I showed the vertical heat exchanger. That's a heat or steam generator, so that I can ensure that is a compact process, because that's a vertical heat exchanger won't occupies more space, floor space, instead of horizontal. Vertical is one of the compact heat exchanger. Similarly, polygen other elements also we can select, so that the minimum floor space also we can ensure by properly selecting the design as well as the components, so that this type of adding this type of feature, the compact units, it's easy to justify the cost of the thermal power generation system. As I mentioned, it meets the multiple needs. Let us say customer demands ABCD. So the ABCD is output. To generate this ABCD output, what type of layout is required, so that we can design the layout. We can design the suitable layout, because I can't say there is a fixed layout. What I showed the earlier layouts is existed in the literature, but we can customize the layout, poly generation layout, to meet the required demands. Let us say smartphone is there. Smartphone, we have many features like 2G, 3G, 4G, 5G. There are many artificial intelligence. These features we are keep on adding by the to meet the expectations of the customer. Because the that expectations are changing, and so to meet these expectations, how to design this device like smartphone. Similarly, the poly generations also we can customize to meet the customer satisfaction, to meet the demands of the customer. Finally, carbon dioxide mitigation is also possible, because if you are using these renewable energy systems to this thermal power generation or waste heat recovery, to this to operate the thermal power generation, the carbon dioxide emission will be controlled, and also this also ensure the decentralized power generation system, so that the load on the grid will also be decreased, because of this more amount of this decentralization of this power generation system. And this slide shows the benefit of this integration, because integration means one type of marriage, I can say. Let us say that solar
వీళ్ళకి అక్కడ
PV.
అవసరం వాళ్ళకి ఇంజనీరింగ్ మా నాది దేవరాజు గారిది అక్కడ పక్కన సైడ్ లేరు. వీళ్ళిద్దరికి కనుక ఏడాళ్ళు కట్టిస్తే పై రెండు వాళ్ళు హ్యాపీగా తీసుకునేవాళ్ళు. వీళ్ళు కొచ్చిలో ఎక్కారండి, మనం అప్పుడు నిద్రపోతాం.
Sorry, please mute.
గ్యారెంటీగా మనం అడిగారు, మీరు కొత్త ఎక్కారు చూసారు.
Dr. Vijay Kumar.
వచ్చినప్పుడు ఎక్కచ్చులేని నేను అలా పడుకున్నా.
Dr. Vijay Kumar.
Sir, we are muting, sir.
Okay. Thank you. The main motivation of this integration into this poly generation is, if you see if you are operating the system separately, let us say there is a system E and system B, the example of power plant and boiler. What benefit we can get here? The system power plant, we are supplying 100 units of energy. LCD has been approximately 36%. If it is 36%, 36 units are converted into the LCD. And similarly, boiler for the heat, process heat, or maybe hot water, whatever it may be, 100 units of energy supplied and 80 units of energy has been recovered, assuming 20% heat losses are there. And the overall energy conversion efficiency, total efficiency is 36 plus 80 divided by 100 plus 100, that is 58% is there. But if the same system is coupled together, integrated together, what we are calling as a cogeneration system, which gives the electricity as well as the process heat 100 units of the energy supplied to this cogeneration system that gives the electricity as well as the process heat. That's 30 units of energy has been taken. Why 30 units are taken instead of 36 miss? Because there is some effect of this integration on this electricity with main product. That's why 36 units has been generated through this cogeneration as per the assumption, and process heat 25 units is taken because the process heat, because the process heat we are generating from the waste heat requirement, because approximately two-third of the energy we are wasting, all the two-third we can't convert into the useful product, because if it is a combustion based exhaust gas temperature, we have to maintain, let us say 150 degrees centigrade of this exhaust gas is required, or 200 degrees centigrade of exhaust gas is required from the engines or the power plant, so that that exhaust gas easily we can escape into the atmosphere through this chimney system. That's why the 100% utilization is not possible. Of course, the loss of thermodynamics, the second law of thermodynamics also is stressing. We can't generate any engine with 100% efficiency. So that's why if it is combined into cogeneration, that's LCD and process 30 plus 55 for 100 units of this fuel supply, that is 85% of the energy conversion efficiency is possible. That means this is one of the promising energy conversion efficiency we can factor, we can expect from through this integration. So, but one more point I want to highlight here: if you are adding cooling system, much more energy conversion efficiency we can expect, even more than 100% efficiency is also possible. Then how to integrate such type of cooling system to this energy integrated energy system, especially for the power generation system, is if you take this example of this vapor compression refrigeration system, of course maybe vapor absorption refrigeration system also we can integrate, so according to the working fluid. For example, this is the energy conversion efficiency or coefficient of energy performance of this cooling system as well as integrated system. If you see the only refrigeration system, the COP is defined as refrigerating effect and work input. In the vapor compression refrigeration system, we are running the compressor, mechanical compressor, by supplying the electricity. So what the benefit we are getting if it is a refrigeration system, that in the evaporator load only, that is which is called as a cooling load. So the COP of refrigerator is QE by W for the compressor. And if it is operated with the heat pump system, is main focus is on the condenser side, that gives the heat. So the condenser heat divided by this compressor load. What is the relation between the that means COP of refrigeration and COP of heat pump? That means COP of heat pump is higher than the COP of refrigerator, which is the +1. That means COP of heat pump is equal to COP of refrigerator +1. If it is a 3 for the COP of refrigerator, we can expect 4 as a COP of heat pump. But if it is integrated to both, that means we are using this cooling system for the air conditioning, for example, and also the heat also has been used, maybe process heat or maybe thermal desalination, whatever it may be. Then what the overall COP or overall energy conversion efficiency for this integration? Simply that is a 3 plus 4, which is a 7. So this critically I am saying 7 is the COP. So far we are assuming that's highest COP we can expect from the heat pump only. But if it is integrated to this multi generation, like both heating as well as cooling system simultaneously, the COP 3 plus 4, the 7 we can expect through this integrated energy system, that COP of refrigerator plus COP of heat pump is possible. So this is one of the advantage to operate the thermal power generation, maybe either using this hydrogen energy as a fuel, or maybe other waste heat recovery as also one of the source of energy we can see. Another advantage of this the poly generation is we can, as I mentioned, the customized product is there. Instead of, if you see the quality, as per our expectations of the quality, the Zebra has both the qualities, like the quality of this load carrying capacity and also the speed, like horse speed also we can expect. So no need to expect the two systems, from the two systems, from the single system itself. That means from one animal we can we are getting the both the properties like donkey as well as this horse. That's a one type of such type of expectations we can get from the poly generation system, which is called as which integrates the multiple benefits. As mentioned just now, it's example of this smartphone is one of the good example to understand the concept of this poly generation. Because and earlier we have phone means only for telephonic purpose only we used to, but now that smartphone has n number of applications like Google Maps, WhatsApp, and internet, camera, audio, video. There are many such benefits are there. Without smartphone, we can't assume our daily life. So similarly, why can't you design such type of energy systems like poly generation system? There are many such agriculture systems. If you see this the tree, that tree has the fruits of uh, apple, orange, banana, such type of agriculture system. That means innovative agriculture system is also is possible with the concept of this poly generation system, like Zebra and Broomstick. Broomstick has multiple applications. This is like a startup, small startup. It has multiple functions. Even lighting, because lighting has, it gives the heat, waste heat. That waste heat has been used to increase the temperature of oil. That's a fragrance. It's maybe room fragrance also we can use. So this type of combination, what it ensures, it minimizes the unused, that means waste heat. Because if you see the air conditioning system, the air conditioning system mostly that's used for the evaporator cooling only, we are using for the cooling benefit. But most of the energy condenser we are wasting in the form of this waste heat. That waste heat is higher than the cooling benefit as per the COP definition. So why can't you use that waste heat, which is we are rejecting from the condenser, so that we can control the thermal pollution? Because that's all the air conditioners once we are running in the summer or the seasons, so that creates a lot of thermal pollution. That thermal pollution can be controlled by properly integrating into the suitable farm. So how to control that, how to use, next question is how to use such type of waste heater, and also how to integrate. Because in while integrating, we have to identify the common features, then only it is possible to integrate. While making the marriage, we have to see the common qualities. If it is a, there is no common qualities, it is difficult to make the integration. So that's why first, at the first we have to identify the common qualities. And the primary concept and primary output from the thermal power generation is the electricity. So the electricity means we have many types of these layouts, like thermal power plants layouts. It's low temperature, thermoelectric effect, direct energy conversions. And once you are seeing this working based system, Kalina power plant, organic Rankine cycle, steam as a working fluid, Rankine cycle. There are many such options we have. So from these options, we can start with thermal power generation using this organic Rankine cycle, or using this Kalina system, or using the steam system, or using gas system like IGCC system. So such that the beginning, first we have to identify the what type of at what level of the energy, that means electricity we are generating, either thermal route or hydrogen based route that we can identify. So next option is organic Rankine cycle is one of the option for the power generation, and still low temperature, even 100 150 degrees centigrade, we have the another option that the binary fluid system. Using this binary fluid system, which is called as, which is a Kalina power system, Kalina cycle. It is a vapor absorption system, reversed vapor absorption refrigeration system. So the merit of this using this binary fluid system, we can design such a system so simultaneously we can get the cooling like vapor absorption refrigeration system, and also electricity in the like a Kalina cycle system. This layout is designed only for the power generation. This layout slightly we can modify into the cogeneration, which is if it is extended to the cooling, that plant layout is called as cooling cogeneration system. So cooling cogeneration system gives the electricity as well as the cooling. That means the output of this cooling evaporator output. And this is a such type of cooling cogeneration system. The components, if you see the components here, all these components are designed for power generation, like turbine. There is a one side is a primary mover, single stage turbine, and this turbine gives the electricity. And after the completion of this expansion of this vapor into this turbine, still that can be used, and further expansion takes place into the throttling valve. So once we are after condensation, of course that vapor has to be condensed. After condensation only we can further expansion takes place in the throttling valve. So the throttling, after the throttling valve, we can expect to get the low temperature, which is below 0 degrees centigrade. That's possible. So this plant ensure the simultaneous generation of this electricity as well as this cooling. That's why this plant is called as a cooling cogeneration system, that gives the higher energy conversion efficiency compared to the individual system like power plant system or the cooling system. There are various components. If you see the components, heat exchangers is a source. This is the generator, the energy source. We have, so outside of this laboratory there is a solar concentrating collector is there. From the solar concentrating collector, that's vapor is generated and expanded in the turbine. Our standby, there is also heater is there. That's a fuel based heating system. That fuel based heating system like boiler, that also generates the vapor indirectly, that generates the vapor that is expand the turbine, as well as it is condensed and subsequently the process has been recycled. That means the cycle is repeated through this various process of combined both Kalina power plant as well as this vapor absorption refrigeration system. Vapor absorption refrigeration system consists of throttling valve, absorber, evaporator, etc. These are another views of this Kalina power plant as well as vapor absorption, integrated vapor absorption system. That means it's not like two circuits, it's single circuit only. The single circuit we can call as a cooling cogeneration system that generates LCD as well as the absorption systems for cooling. And in the trigeneration system, not only LCD and cooling, we can also add one more system like desalination system. So if you see this, because the waste heat recovery is there, once you are generating LCD, that LCD has two-thirds of the energy is wasted into the form of this hot gas. That hot gas can be recovered to the process heat as well as this thermal desalination. In this thermal desalination, one of the thermal desalination here, HDH desalination we integrated here. That HDH desalination is a humidification, dehumidification, because this humidification, dehumidification has a common features to this air conditioning system. So this air conditioning has mostly that air is getting humidified, dehumidified, cooling, heating, reheating, etc. takes place. So the similar process we can generate, so that's into the water cycle, which is that water cycle artificially we can create. So simultaneously we can get the cooling, which is like cold air for the air conditioning system, and also the and also for this water purifier. So water purifier, this water purifier is used for the this water purifier gives the electricity. This water purifier gives the desalination, and this combined system gives the electricity. This is the electricity we can see, and the green color shows this electricity, that turbine, and left hand side these reactors, that's especially for the humidifier and dehumidifier, that gives a condensation for the water purifier. And also like a byproduct I can say that cold air is also is coming from this plant. This is a one trigeneration plant. Through this trigeneration plant we generated the electricity, water, and the cooling. This is the system, that's integrated system. Turbine is there for the power generation, and vapor absorption components is there. This vapor absorption components gives the chilled water. That chilled water is used for condensation of this humid air. So the condensation of humid air is resulting the potable water and also the cold air. So two outputs with one process is possible with this type of this HDH cycle. Yeah, this is the heat pump based poly generation system. This heat pump based poly generation system, it is redesigned into the vertical model. Because in earlier slides, if you see, the mostly it is the horizontal orientation is there. Horizontal orientation it is fine, but it occupies the floor space. So once we want to design that compact design, like heat pump based compact poly generation system, then that all the process has been designed into the vertical duct. This is the vertical heat exchanger. In this vertical form of this heat exchanger, all these heat exchangers, that's air heater, air preheater, and the humidification process and dehumidification process, all has been arranged in the vertical. So it can be fixed as a wall mounted system. What drawing shows this two-stage system. For the single stage system, much more compact we can expect from this process. So this compact size can be wall mounted, can be, we can design so that that gives the all the benefits like what listed here: the electricity, drinking water, space heating, space cooling, hot water. Hot water means so that this system can, it replaces the geyser, because we are using geyser for the hot water. So geyser can be replaced, and we are getting electricity from the grid. So it's so that we can generate the electricity like a self generation mode. And water purifier, it also replaces the water purifier, because we are fitting the water purifier at the wall that gives the drinking water. So water purifier also we can replace by means of this poly generation system. And we need the air conditioning, not only air conditioning and heating process, especially for northern cities. Here the temperature is low, it's even close to 0 degrees centigrade will come. That time we need to operate the system at the, to maintain the temperature, comfort temperature, like 20-25 degrees centigrade. The heating is required. So such type of heating, which is air heater, heating is also is possible from this poly generation system by simply switching to heating mode or cooling mode. So many such systems like geyser, water purifier, electricity, and air conditioning system, and air heating system, all these components you can see into a single product. So one product gives this replacing many such systems. So you can see this experimental development of this power generation system, which is in the vertical model. So that the design of this vertical model, that floor space, it is minimized. It is a research model, that's why it looks like bulky two-stage system. For commercial, it may be much more compact system we can design, so that the single stage commercial model is more comfort to install. It is easy to install such type of systems. Also, we can design to get more commercial viability of this type of research work. So at the laboratory level, if you see that heat pump system, that heat pump system is a water cooled system. Generally, air conditioning system is a condenser, is a air cooled system, air cooled condenser. Instead of air cooled condenser, if the condenser is designed with the water cooled system, so that hot water we can generate. That hot water maybe that like a, that can be used as a geyser. So that generally geyser means once we are supplying 1 kilowatt of electricity, we can expect 1 kilowatt of heat, neglecting the current losses, copper losses. But if you are supplying 1 kilowatt of electricity to this type of heat pump, that gives, if it is a COP is 4, for example, theoretically I am saying, that generates the 4 kilowatts of heat. That 4 kilowatts of heat is much higher than the 1 kilowatt of heat what we are getting from the conventional geyser systems. So in terrace, it is connections are there. That means a storage system. This is a storage tank, hot water storage tank, and there are so many plumbing system. Actually, this plumbing system we incorporated to get the more flexibility. That means without incorporation of the solar energy, or with the incorporation of the solar energy. And there are many options like single stage mode of operation, multi-stage mode of operation. I hope you are seeing this what I am playing this video. Dr. Vijay Kumar, can you confirm whether you are able to see this video play or not? Dr. Vijay Kumar?
Yes, sir.
Okay, okay, thank you, madam. So if you see this vertical mode of operation, this vertical mode of operation, what benefit we compare to earlier practice is the floor space. One is the compactness, and second is the floor space. And another benefit of this design is it's easy. That means all vertical heat components like heat exchanger, easy flow of fluids, like easy flow of water and easy flow of air is possible. Like once through system, this once through system ensures the easy flow of the fluids, and also condensation rate also. That condensation rate also is increased because of the minimized obstructions. Because once we have so many bends at the curves, and there is a lot of losses are there, curved losses are there. So minimum losses of these hydraulic losses are the fluid losses, that gives the minimum pressure drop of these fluids, both this water level as well as this uh, water level as well as this airflow lines. Such type of benefits we can get by integrating such type of vertical systems. But before installation, or before going to fabricate these type of models, poly generation models, first of all we have to plan thoroughly, because the design, nearly 80% of the research development is the design process only. Remaining 20% of the development is the manufacturing. More focus we have to give on the design, because if the design is perfect, we can expect the making, that's manufacturing according to the design design of the product, that's dimensioning what we have. If the design is failed, that manufacturing also it will fail. That's why most of the work we focused on the design of the system, design and the optimization of the system at various routes like modeling. These modelings also pre-design modeling, post-design modeling, the simulation of the model, and the analysis, the post-design analysis and pre-design analysis. All these, including optimization, all these components are integrated together. Finally, it gives the operating conditions, favorable operating conditions. At the favorable operating conditions, we can design the product and we can design the system so that we can ensure that success, that means satisfactory operation of the plant. Otherwise we can't expect the yield, whether the yield is as per our design, as per our expectations or not. That can be ensured that, by properly designing of the system. That's why at the beginning we have to check all the process conditions whether it is feasible or not, because sometimes some of the operating conditions may not be feasible. That's why we have to identify what operating conditions are feasible and what operating conditions are not feasible, so that we can design the system and the feasible operating conditions to ensure the satisfactory yield in all the outputs like power generation, drinking water, and subsequent process heats, etc. Another design is here. It's very compact. If it is single stage, is more compactness we can see. Like if you see like a window air conditioning system, and the window air conditioning similar to the size of window air conditioning system, the poly generation also can be designed so that in the same place, within the same place, we can integrate this desalination process and air conditioning process and heating geyser, so that that box or that component will give the hot water and cold water, drinking water, and of course LCT if it is integrated with the solar PV system, and that is LCT and products like what we mentioned, drinking water. So this is the one type of compact design for this power generation system. And subsequently here we also extended the works on the focusing of the collecting system, solar collecting system. In the solar collecting systems, we integrated this PV system as well as the thermal system. It is a prototype actually. Recently we installed the large size solar PV system. It's a 6 meter square solar thermal and PV system that ensures the LCD generation which is required to drive the systems. At sometimes we have to operate the pumps, and sometimes we have to operate the fluid even in the receiver of the thermal collector. So we minimize the usage of LCD to drive the collector, especially for the tracking system. So the tracking system, once you are using the other than LCD like the gravity system, these gravity systems will ensures that operation driving of this collector. This is a prototype driving of this collector with this gravity system. So the gravity has means that is the storage energy. LCD means that we have to supply the current to operate this collector. Once you are saving that LCD, we can expect more efficiency from this net efficiency. I'm saying from the system collecting system. So either storage energy, the kinetic energy, the spring energy, or gravitational energy. These are the various forms of other energies other than this LCD power free tracking system can be designed. So this source has been integrated to this thermal poly generation, so that the further enhancement of this energy conversion is augmentation of this energy conversion is possible by properly integrating such type of solar collecting systems. So these solar collecting systems can be integrated to even for the hydrogen generation or such type of poly generation systems. So it's a modeling, as I mentioned. the design of the system. Before going to integrate testing of such products as the process, first thoroughly it has been verified with the models like mathematical models, engineering mechanics models, so that gives the some the complete picture, clarity of this operation. Because in the field many questions will come: how much water is required to control the system, how much gravity force is to be applied, what is the size of the thermal collector, and what is the size of the PV collector. All these questions can be sorted out in this design and modeling of the system, so that that simulation and optimization will use a proper best operating conditions to get the satisfactory level of operation of this power generation system. So finally, I want to conclude that thermal power generation has great flexibility, that it leads to more innovation, and whatever the ideas we have that we can implement without hesitation. But thing is, before going to implement into the laboratory or the commercial level, first of all we have to check all the levels of feasibility, the technical feasibility, economic feasibility. All these things we have to check with through the thoroughly the design and the proper modeling system and optimization system. Then we can expect the successful demonstration and successful launching of such ideas and the products and the process into the commercial level. And as per the results, the double stage system, desalination system into this power generation is giving the more outputs, but compared to the single state is fine. But thing is some penalty. We also find some penalty in the double stage operation, in the energy conversion operation. So that if the customer, sometimes customer will say, I need the yield, not the efficiency, energy conversion efficiency. So we can recommend the double stage. If the customer is expecting more efficiency than the yield, then we can go for the single stage operation. So such type of decisions, what type of model we can suggest depending upon the requirement of the application, because application to applications the requirements may change. Such type of decision making effectively we can take by properly designing of such systems. And process conditions also, the optimum process conditions, like while designing the cooling system, here we notice that evaporator temperature is one of the key parameter that can be optimized, so that maximum energy performance ratio, the maximum energy performance ratio is possible by properly optimizing this operating condition. What we identified is the evaporator temperature at 10 to 15 degrees centigrade. We notice the maximum benefit, of this power generation system. And also, due to temperature losses from the concentrating collector, a binding fluid power generation results low energy performance ratio compared, because there are many type of power generation system. Let us say IGCC, integrated gasification, IGCC based power generation system, and binary fluid based power generation system, heat pump based power generation system, ORC based, organic Rankine cycle based power generation system. Binary fluid means Kalina cycle. All these options, maybe 5 options or 6 options, can be compared together. We compared to only here what in this presentation. All many types of these routes can be compared, so that the best layout, and the suitable layout also, of course suitable layout also we can see that we can take the right or correct decision by properly comparing various layouts of this power generation system. Finally, the energy performance ratio, we can expect more than 100% also is possible, but properly, if it is integrated with the cooling system only, it is possible. Otherwise, if it is not integrated with the cooling system, we can't expect the crossing of this 100% of this energy conversion efficiency through this poly generation mode of operations. So finally, I thank this government. What are the funding I received from CSAR, DST, to convert these ideas? What are the ideas for solar collecting system and storage system, or the utilization, especially for the polygeneration mode? Polygeneration mode of operation. I thanks to the support, ministry support, for the demonstration of these ideas into the reality at the laboratory level. Of course, maybe in commercial level also in future. And I thank all the participants here for this listening this lecture, and your patience and constant focus what I am explaining this various routes of this hydrogen generation, especially for the methane reforming, cracking systems, and
Yes.
shift reactions, and usage of this such type of concepts in this gasification IGCC operation and thermal recuperation and combined cycle system and fuel cycle system, and extension of this utilization into the poly generation mode. And thank you one and all. It's time to interact. I'm happy
Srinivas
to.
sir,
Yes.
thank you sir. Thank you for delivering a nice lecture to the participants on hydrogen applications in poly generation and other various aspects in this one. Thank you sir.
Thank you.
Now it's time to open the videos of all the participants to take a snapshot with our resource person. Dear participants, please ask your queries. Sir, no one is responding,
Okay,
sir.
okay, Dr. Vijay Kumar. Okay, fine. Just share my email ID. Maybe if they want, they can ask, reach me.
Okay. Sir, can you please provide the PPT, sir?
Yeah, I will share now. Closing this.
Okay, sir.
Thank you, one and all, once
Thank you very
again.
much.
Okay, bye.
Bye, sir. Thank you, sir.
Thank you, sir.
Thank you, bye.